How does adiabatic quantum computing relate to statistical mechanics? Imagine a quantum system slowly changing its shape, trying to find the lowest point in a complex landscape. That's what adiabatic quantum computing does, and it connects deeply with statistical mechanics. In simple terms, statistical mechanics is about understanding how large groups of particles behave based on their microscopic properties. It explains phenomena like temperature and phase changes. When we look at quantum systems, the rules get a bit more specific, focusing on how particles occupy energy levels. Adiabatic quantum computing starts with the system in a simple state, then gradually transforms it into a more complicated one that contains the answer to a problem. The goal is to keep the system in its lowest energy state, called the ground state, throughout this process. This is similar to slowly lowering a ball into the deepest part of a valley without it bouncing out. Now, statistical mechanics helps us understand how likely the system is to stay in that ground state. It uses concepts like energy gaps, which are the differences between the lowest and next lowest energy levels, and temperature, which influences how particles jump between states. If the temperature is too high, the system might jump out of the ground state, making the computation fail. Tools from statistical mechanics, like partition functions and density matrices, help describe the quantum states during this process. These tools show how environmental factors, such as thermal noise, can cause the system to behave differently. This is important because real quantum devices operate at finite temperatures and are affected by noise and decoherence. Quantum phase transitions are another key link. These are points where the system's ground state changes suddenly as we tweak the Hamiltonian, which is the mathematical description of the system's energy. Near these points, the energy gap can shrink, making it harder for adiabatic quantum computing to succeed quickly. Statistical mechanics provides the framework to analyze these transitions and predict how the system will behave near critical points. In practical terms, adiabatic quantum computing can be used to solve complex optimization problems, like finding the lowest energy configuration in spin glasses or tackling large combinatorial puzzles. It can also simulate many-body quantum systems, which are important in materials science and chemistry. So, in essence, adiabatic quantum computing and statistical mechanics are linked because both study how systems behave at different energy levels and temperatures. Statistical mechanics offers the language and tools to understand the quantum states, energy gaps, thermal effects, and phase transitions that influence how well adiabatic quantum computers work. This connection is helping us develop better quantum algorithms and improve the design of emerging quantum technologies.